Meeting is being recorded.
Okay, so today I'm going to give a little bit of an introduction on the work that we are starting to upstream, specifically the work that talks about the fission interference graph, which is a graph that we want to use for loop distribution or loop fissions. And it's based on the work that Bardi has done, DataDependence Graph. So it's an extension that is a consumer of the DataDependence Graph. So it's probably going to take about half an hour or so. This is just an introduction. There is a pull request that I have put out, I think maybe a couple of weeks ago or so, on the first portion of the code. And with an outlining in that same pull request of kind of like a little bit of a plan of what the subsequent pull requests are going to add in terms of functionality. And some of you have already started to review that pull request. And, I'm going to spend some time to take the feedback and then address what I can. So this is just to give a little bit of an overview of what this thing is supposed to do. All right, so let's see if I can change slide. So here is a motivating example. So we have a loop that on I that goes from 0 to n, where we have a number of array accesses in 3 different statements. So the first statement to say is A, D, and D as the next element, and the array is D. And second access again, the same array element as the first one, B. So B, C, D, and E are accessed also by the second statement in the loop. And then the third statement in the loop, it will reuse again the element B sub I and nothing else. So I highlighted here essentially the data reuse between statements. Some of them are temporary reuse, and there is a special reuse for D and the I+1. So we can observe by just looking at this code that there is common data access between the first statement and the second statement, and quite a bit of reuse between those 2 statements. And then there is a little bit of reuse between the first statement and the third statement, and also the second statement and the third statement due to the access of B sub I. And also we can count the number of, these are all stride 1 accesses. So we can count the number of accesses for this array, and these are called data streams. And if we count them, we see that in total, the entire loop contains 12 read streams. So we're reading stride 1 accesses in this array. And we count, for B, we count the stream only once, because essentially even if you have multiple accesses to the same array, that's the same stream. And then we have 3 write streams. So if you look at this loop, the question is, what limits the performance of the loop, if anything? And so that's the question I'm going to try to answer for this presentation, then try to provide a mechanism to model what this loop is doing, and then essentially try to improve performance. So observation is there is stride 1 access, and they have good cache locality, and there is quite a bit of reuse between statements. Those are all positive things for this loop exhibit. The not so good thing is that we have a lot of data streams in total. We have 15 data streams that are used in this loop, and they consume, like in certain architecture, and power architecture is one of those, data streams are being tracked by the hardware. So whenever the hardware determines that there is a stride 1 access inside the loop, like in this loop, it will track the access to stream data from L3 to L2 to L1 cache, so that when you go to L1 cache and try to access an element, it would have been streamed down from the memory hierarchy into the higher, either in L1 already, or if you miss, you're gonna find in L2. So the limitation here is that the hardware, in our case, can only track up to 8 data streams concurrently per loop or per loop nest. And so because we have 15 data streams, this is not ideal. We would like to have less data streams. And if we did have less data stream, what happened? this is what we observe. So how can we have less data stream per loop? Well, the answer is we can distribute one or more of the statements into separate loops, and that will, in this case, limit the number of data streams that are used. So if we count the data, so we have distributed the last statement into a separate loop. And we have chosen the last statement because we want to preserve the maximum amount of data reuse between the first two statements. And so we want those two statements to be in the same loop to still have good data reuse. And put the last statement, which has only little data reuse, into a separate loop. If we do that, then we still have common data access between the statement in the first loop. There are 8 data streams that are used in the first loop. 2 are write and 6 are read. And the second loop also has 8 data streams. So we are in kind of like this ideal situation where we do not exceed the maximum number of data streams that the hardware can track. And if you go and look at the CPU cycles that are spent into the original loop versus the second loop, we go from almost 100,000 cycles for the first loop down to about 60,000 cycles in the second loop. So we have almost between a 30 and a 40% improvement in runtime performance due to this transformation. So that's the benefit. So this is an example where loop fission can be used to improve runtime performance. In this case, because it can reduce the number of resources used by the original loop without compromising too much the opportunity for data reuse. So there are 2 conflicting kind of heuristics here, right? One is like we want to keep some statements in the same loop because we have affinity between statements due to data reuse or other consideration, but in this particular case, data reuse. And on the other end, we want to keep them separate because of resource consumption. And resource consumption in this case is hardware streams. It could be amount of register pressure. It could be the number of the code size. It could be a number of things, right? So we want to model these into a graph. And that will be the affinity graph that we are working on. So to create this affinity graph or this interference graph, we start from what we already have, the data dependence graph. So if we look at the printout of the data dependence graph, and this is already, I think, is fully upstream. There is a way we have a printer. So if you can get the data dependence graph, we're going to have a printer that can print this graph for you. So that's where we got this thing. So the first part of the graph represents the first statement. There are a number of nodes. Some of the nodes produce a value, and then the value is consumed in other nodes. So the edge that is labeled diffuse represents the relationship between the node that produced the value and the node that consumed the value. So it's called a diffuse edge. And then in some cases, we also model where there is a memory dependence. The edge is going to be a memory edge. And so on. It's done. The same thing is done for the second statement and the third statement. And you can observe that the 3 set of statements are independent with respect to each other because there is no edge in between them, right? While the first statement can actually be collapsed into one. So this is what we do when we, sorry, I have to go back one. When we create the interference graph, we take the data dependence graph and create a new graph here where we have merged nodes that can be merged without breaking dependencies. So in the first case, we have merged all the diffuse and memory dependency into the consumer node. And so we have increased the granularity of the consumer node. We have reduced the number of nodes that are necessary to represent the program. And in this very simple example, we are left with no edges because all the edges have been eliminated by merging the data dependence graph node into a single interference graph node. So that's what we do. And this tells us that it's actually legal to distribute the 3 nodes because there are no edges in between them. So we could, at this point, get this initial interference graph and then distribute it in between into 3 different loops in any order. There is no, that there would be a legal transformation. That's how we know by inspecting the interference graph that that's a correct transformation. So the question is, we can do that, but is there a better way to distribute this graph? Right. So in the initial interference graph, we have not yet modeled the data reuse or the stream consumption. So what we do after we have created this initial graph, we actually we have some analysis to detect the number of streams that each node uses. And so we annotate the nodes with resource consumption. In this case, it's just the number of streams. And we observe that the first node uses 6 streams, the second 8, and the third 6. So that's the stuff that the label in red, that's actually a property of the nodes. And then we create affinity edges. So these are edges that represent the desire to keep 2 nodes, the nodes they connect together. So these are weighted edges, and larger weight indicates more affinity. So the larger the weight, the more is the desire to keep the nodes together and merge them. In this case, the affinity weight is computed by observing the amount of data reuse. So if we take the node number 8 and node number 7, so here is 8 at the top left corner, node number 7, we can find that there is a number of reuse between different arrays, and that's how we compute the weight on the edge. The weight is 5 because there is 5 data reuse for between these 2 statements. So once we have this graph essentially represents a model of the reuse and the resource consumption for this program. And what's left to do is to try to partition the graph into subgraphs or regions that present large affinity, but they do not exceed they don't use too many resources. So there will be a resource limit. It's kind of like model on the target architecture. So there are different partitioning strategies that can be applied. One simple one is to go through the graph and try to determine which is the affinity edge that has the largest weight. So greedily try to merge the nodes connected by those edges. So if we were to apply that kind of strategies, we go through the first 2 nodes. They have weight 5. Those are the nodes that we want to merge because all the other edges have lesser weight. And when we merge them, or when we try to merge them, we try to figure out if we are exceeding the resources. So in this case, we have 6 streams used by the first node, 6 streams used by the second node, but some streams overlap. We can detect that. So we infer that by merging these nodes, we are going to use 8 streams, and that's actually still within the limit. And so we would go ahead and merge those and repeat the same procedure again until there is nothing else that we can merge. And they'll give you the final interference graph. And after you have the final interference graph, you can then distribute the nodes into different loop nests. So that's one possible partitioning strategies. Of course, there are other partitioning strategies. For example, one may want to say, well, if I merge these 2 nodes together, then I'm going to prevent a further merge to happen. And if I were to merge this other node instead first, they'll give me a better result at the end. So it's kind of like there are algorithms, well-known algorithms, for trying to minimize the flow or the weight of the edges that separates different partitions. So a mean flow, max flow, mean cut kind of algorithm would be one that is potentially applicable to this kind of problem. All right, so that's what we try to do. Like I say, in this case, if we roll greedily, we're going to merge those nodes. And if we did that, it's actually, this is what happened. This is how we got the reduction of 35%. I don't remember exactly in CPU cycles. And also we know that the L1 data cache load misses is reduced, and the store miss is also reduced. Essentially, we are utilizing the memory subsystem of the target architecture more effectively because the hardware is able to track all the streams inside in the loops, in the two loops. So that's essentially what I have in terms of introduction, and I would like to open the floor for questions or comments on what I just presented, and if you have idea, I would be happy to of course listen to you.
Okay. Thank you, Ettore. Any questions from the audience?
Thank you, Hector. I have a question. So the dependencies inside the fission interference graph, so they are taken from the data dependence graph. So is there are these all the dependencies of the data dependence graph, or all just a subset, some that you can ignore in the fission interference graph?
Yes, there are some dependencies that are actually ignored. So that's, let's say, that's a partial view of the data dependence graph. So in some cases, we are not interested. So the data dependence graph is going to contain dependencies that are caused by scalar variables and not just memory accesses. It also encodes dependencies due to the induction variables that create cycles and so on. And those are not interesting dependencies for for the interference graph. So those are actually ignored. But the dependencies, the memory, all the memory dependencies are actually tracked. So I would say the initial interference graph represents a subset of the data dependence graph. And of course, it goes without saying that if we had a program dependence graph, then we would be able to track the program dependence graph as well, and that would allow us to encode, to reason about loops that contain branches in them. Right now, we just have the data dependence graph, so that's what it does. And then later on, it's going to merge nodes to try to increase the granularity before you go ahead and start to encode the heuristic that you're interested in.
Another type of dependence that is somewhat ignored is the input dependencies.
Yeah.
Like if you consider the store to the A and store to F, both of them have reuse between BI. But BI is an input dependence from the first statement to the second one.
Right.
But it's not imposing any ordering or preventing distribution, which is why it's safe to ignore.
Right. So input dependencies are not necessary to encode for legality purposes.
Right.
Okay. Yeah. Wait for a moment. The data dependence graph includes dependencies induced by induction variables.
Right.
That would be new to me.
It has edges between.
I mean, if you do that, you have always a cycle because the induction variable always depends from. So you have I equals I plus 1 for getting the next one. So you would always have a loop carry dependency.
No, well, it's not. Okay, so there is a diffuse dependence, which if you really want to, you can treat it as a scalar dependence. And yes, in that way, it is like a loop carry dependence. But because it's all contained within the diffuse chains, it's not actually including the loads and the stores that use the induction variable. So yes, you always have this circular dependency and you have a pi block, but it only contains the induction variable and things that are derived from it, not the loads and stores.
Okay. And the input dependencies. First, I know also I looked in the source of memory dependence. For pure input dependencies, it does not report for there being a dependency.
The DDG should report it, but the interference graph here ignores it.
Yeah, I've seen this in Hector's patches, but I think so. The data dependence graph uses the dependence info analysis to generate its edges. But if it I looked it up. I think the memory info depends function returns null if there's just an input dependence. So such a dependence would not even be added into the data dependence graph. Or am I wrong there?
You're right, depending on how the code is generating. Like if there's a separate load of BI for the first store, and then another load of BI, in other words, the LLVM value is not being reused, then they're separate loads and they will be input dependencies. But the dependence info is structured such that if you say the source and destination instructions are the same, it will say there's no dependence between them.
Right. So if you redundantly load the same array elements in different parts of the block, then that corresponds to our input dependency. If you were to reuse the first load, because it is redundant, then obviously there is no new load. Right. So there is no new node for that load in the data dependence graph.
Right.
Okay.
So that's the way it is. Like, so yeah, it would be interesting to see whether we actually do need to try. I mean, the data dependence graph is very exhaustive. It represents every single thing that happens into the loop, like all the scalar accesses, all the diffuse between scalar variable, all the memory dependence, input dependence, everything. So in my case, I don't need all those things to solve this problem. Perhaps there are consumers of the data dependence graph that they would need. Like, for example, to compute the hardware streams, you are actually interested in input dependencies because they represent reuse. So it's, you know, I can get them from the data dependence graph, not for the purposes of legality, but for the purposes of, you know, heuristic purposes to find out what are the streams, what's the amount of reuse, and so on.
Mm-hmm. Okay, then.
So they become useful in that context, but they may not be useful in some other context, right?
Right.
So if at least in the data dependence graph, if there are such input dependencies, wouldn't it also cause that nodes would be merged into pi nodes so that you couldn't even differentiate between the different dependencies?
So for it to be merged into a pi block, there needs to be other edges that connect it back to the load that initiated, like that the load that's the source of the input dependence. So if there is such a cycle back, yes, it will become part of the pi block.
But that would also mean the loop, the fission interference graph could not fission those anymore because there's the input dependence.
That's right. So that's a kind of like yeah, I forgot. So the fission interference graph nodes currently they represent what we call simple DDG nodes and also pi blocks. So they don't expand the pi block that the DDG has. They just represent it as is. So it is impossible currently to go and split the pi node into different interference graph nodes.
Yeah, in a way that's a benefit of the design because we intentionally wanted to make sure that we don't break circular dependencies because that would result in incorrect transformations. There are techniques to break cycles. When the DDG is formed, all those transformations are expected to have happened, yes. And therefore the DDG is a true representation of all the dependencies in your program.
Yeah, you could rematerialize the load. If for example, if you had one load into a sub-I and then the next statement uses that same, you store load say sub-I into a %2 and then somebody else uses %2 in multiple places in other statements, then you're kind of like limited to keep that %2 to the one that produces the value in the same loop. But you could rematerialize, if you really wanted to distribute the other statements, and that was prevented distribution, you could rematerialize that load.
Yeah.
As long as nobody can store into it. That's not what we do. So we would rely on, previous transformation to do that for us before we go through the code that does the distribution.
Yes, and there are other transformations such as scalar expansion, that extend scalar dependencies into non-decay dependencies. But like I said, when we build the DGG, we assume that the program is what we have, and we model all the dependencies there. And then if you have a cycle anywhere in that graph, you cannot safely distribute nodes within that cycle. And that's what this interference graph does.
Excuse me. Sorry, the sound is deteriorating. I can't understand anymore.
Sorry, Jimmy, are you trying to say something? I think the noise comes from you. We cannot hear you well.
Is it better now?
A little bit, yes.
Okay, I have a question. Probably I missed something very basic. So in this picture of DDG between node 15 and 16, they seem to be. I mean, I expected that load. I think they are the same load, right? That's the BI that is reused by both statements. So how I expect the load to be eliminated by the time that we want to construct DDGs. That is not the case.
Okay, so the IR would have two loads for BI. Although the different statement access is a byte, the IR that was presented to distribution in this case would load BI for the first statement and then load BI again for the second statement. That's why the data dependence graph has two loads that are indeed redundant in this case.
Actually, they have a redundant get element pointer too. If you look into
they also have other stuff.
BI and BI2, and BI2 actually is a different redundant get element pointer.
Now, if the load was not redundant, then there would be only one load in the DDG that feeds both the store into A and the store into F eventually. And so those two statements would then be using the same variable. Now, if you wanted to distribute these two statements away, you would have to rematerialize this load into the two loops. So for distribution, this is actually a better situation to be in because you can clearly see that the two statements are independent. Now, if there was a dependency on the same definition, then you would have to generate the definition for both nodes somehow, right? That's something that we're aware of. And there are indeed cases where these loads are common. Does he answer this question, Jimmy?
This is Elson, by the way. I'm using Jimmy's account, but
I should have recognized your voice. No,
yeah, I'm not sure I fully understood. So you want to rematerialize the BI. So we know that BI is not aliasing with AI. I kind of make that assumption.
Yes.
But then we want to rematerialize BI to make distribution easier, which makes sense. But how do we do that when that happens?
So the transformation, the distribution doesn't do that at all. I'm saying if the IR happen to be that way, then we can take advantage of it. There's no transformation yet that can rematerialize this load.
Okay. Okay, thank you.
You need to do the opposite of commenting, essentially.
Yeah.
Yeah, you have to do exactly. So if you run commoning before distribution, for example, then that would limit your distribution opportunity because of this. This could be one of the reasons.
Put them together.
So you would have to do, I don't know, copy propagation, or like essentially duplicate that value.
Yeah.
Now you would have only to do that if it happens to be that you want to distribute those two statements in different loops. If you don't want to distribute the two statements in different loops, then there is no need. That's like Varga said before. This kind of thing, these kind of things are kind of prerequisite right now. So that's the kind of like design that we are following, such as we don't want distribution to at this point to worry about scalar expansion, which could also allow you to distribute more things.
Okay.
Like we don't manipulate the IR. This is kind of like analysis. We build this graph, and then the consumer of the graph, which is going to be loop fission, you could have a loop fission that either takes the graph as is and distributes it, or it may use the information in the graph to notice that there may be more distribution opportunity by doing rematerialization and stuff like that. Now, of course, you have to strike the balance between what the transformation itself is prepared to do. It makes it more complicated. Or it's better to design other transformation that can expose those opportunities. It's kind of like, in some other cases, we have transformation that they won't run because the IR is not ideal, and they need to run something before then to provide the opportunity.
So basically, we need to we would need some sort of preparation before loop distribution to. I'm trying to see if I understood you correctly at a high level. So we need some preparation to basically replicate some of the instructions or undo the commoning to be able to get a good DDG and a good interference graph.
So that's one potential strategy. I mean, this is all open for discussion between the group, right? That's one potential way to do things. The other potential way is to add more intelligence to the transformation itself, make it do more. There are pros and cons, right? Like, not, at this point, we've chosen the way as a first pass to go with the simpler approach.
And the simpler approach is
see later on. It's also more understandable to review. It's cleaner, right? It's already complicated on its own, but if we start to add too many features, it becomes very hard and can become messy very fast.
And just for reference, this particular simple example is run with O0 plus the loop simplify and loop rotate. Only the necessary passes to make the loop in certain form and then run loop fission.
Yes.
That's why comments of expression is not run. That's why they are still two statements.
Yes. So it may. Yes,
yeah. So I guess the point is that we just build the interference graph and then use it for distribution as is, and then if we find out that there's additional cases that we're not getting because the IR is changed in some way, then we can decide whether we build that complexity into the interference graph or into distribution or into something else that massages the interference graph prior to distribution using it. Does that make sense? Yeah. That would be follow-on work. Getting the basic infrastructure in and working is the first step.
And so, basic infrastructure first, then start to add the ability to find reuse. So, Affinity Edges find the ability to express node resources, and then the partitioning strategies. They're kind of like the way that we are working toward. Now, there would be things where, there is different kind of resources that you can use. So we're looking at streams and code size. somebody may want to add register pressure.
Yeah.
We're not looking at that right now because it's very hard to estimate the register pressure enough at that level. Right? I mean, the big light variable would be one that we can consider. And this is one of the potential things. We have not yet looked at vectorizations, which is very important. Distribution can be used to expose vectorization opportunities. We don't have a short-term plan to look at that, although it's perfectly clear to me that we would have to look at that if this was to become powerful enough to replace the current distribution pass in LLVM, which only does vectorization, as far as I know.
Okay, so you probably already said this, I may have missed it, but this extra complexity that we need to add somewhere and we don't know where we want to add it as far as, is that something that part of the code that you plan to upstream as you continue upstreaming your loop distribution, or that is not included?
I plan to stream like if you look at the initial pull request, there is a little bit of an explanation of what the patches, the kind of feature that I want to upstream, right? So the first is the basic infrastructure for loop for the efficient interference graph. Basic infrastructure means nodes, edges, only the type of, the ability to use the data dependence graph, the ability to create what we call maximal distribution. The second pass would be to add the ability to track reuse, and so that would add affinity edges. And then the ability to add the concept of a resource consumption to a node. And probably the first resource consumption will be hardware streams. And then within the node resources, you can track different type of resources, right? So you can have a class called node resources. You can add more type of resources. The type of edges, you can extend edges. You may want to add an edge that represents, the opposite of affinity. I do not want to merge these nodes ever. Like for example, if the two nodes, if you were to merge them, they create an imperfect loop nest, you may not want to merge them. And then the code will be, the efficient interference graph is going to take heuristics. So, for example, say, well, try to encode this type of resources, this type of partitioning strategy, and so on. I'm trying to make it modular. Of course, this will get feedback from the community, and then the idea is try to make it modular so that you can use it for different purposes, right? And potentially a different point in your transformation strategy. At some point you may want to call this to vectorize, and some other point you may want to call this to create perfect loop nest, and so on.
I see. Thank you very much.
Well, we are not really working on these other passes that, like do scalar expansion. If somebody wants to work on a scalar expansion path, then there may be complementary work to this kind of PR we'll do.
I see.
Okay, thank you, Ettore. Any other questions from the audience?
Hi. This is Brian. I was wondering, Ettore, would you be able to share this slide deck with us?
Yes, we can.
So this call is being recorded. I can send the recording to the foundation and ask them to put it on YouTube.
Yeah, if you want to. I don't have a problem sharing the slides.
Okay. Recording is fine. It's even better. Yeah.
A little bit of self-publicity. There is an accepted talk at the Nest LLVM Developer Conference in April, where we have a talk on loop fission. So part of the things that I'm doing is to give you a little bit of a preview. There'll be more, obviously, that is going to be maybe more high level and with some extra information. And hopefully I can see some of you guys and at the conference, and we can maybe have a deep dive by that time you would have seen some of the code as well, right? So we can have a round table or something like that for people.
Great, thank you.
Okay. Thank you very much. If there are no other questions, can quickly go through the status update. So in terms of the data dependence graph, thanks to Michael, we had all the functional changes approved. The next batch I have is one that adds a dot printer and another one that adds more tests. I'm planning to work on that in the next few weeks. As for the delinearization of constant size arrays, thanks again to Michael, that got approved, the main part of it. The renaming of the option, I think you're gonna draw that. And then loop distribution, that's what Ettore was talking about. There's a patch. Please feel free to review it. We would appreciate comments.
I got some comments, and you know, thanks to people already from my side.
And what about loop nest analysis?
It's been approved. It's ready for landing. I'm trying to push it in soon.
All right, and then for Unroll and Jam, with me?
I get to reply on two strategies. You can take one from Vardy and one from Michael. And I want to see the owner of Loop Fusion opinion, which is Kit, before I choose whichever point.
I know I owe you a review.
Okay. Okay, so we'll come back to it next time. All right, so for the next meeting, I don't have anything on the agenda, but I would appreciate if you let me know if there's anything you want to discuss. That would be nice. With that, if there are no questions or updates from anyone else, we call it the meeting.
I would have a comment. So just for general, like the efficiency of the algorithms I've seen. So there was some the simplification of the DGG and now the fission interference graph. From the asymptotic efficiency, like the O notation, they were quite, let's say, suboptimal. So in this case, for the fission interference graph, it's so we created the data dependence graph once, and one could just once it's created, one can just traverse the dependence. The data dependence graph to create the fission interference graph from, instead of iterating all the nodes, all pairs of nodes again, and to see whether there is a dependency in between them. So usually said I'm not sure where I found somewhere so n squared in complexity is just not bad enough to be obvious from simple examples. So it might slip through in production, but when you hit it in production, you will see it's easy to hit them, especially when you start to try to optimize larger function where you have thousands of instructions. Then you had an n squared complex algorithm, you will notice that. So that's one of the reasons.
So that's one of the reasons that we're trying to. I mean, it's no need to represent all the fine-grained nodes that are in the DDG. And that was one of the intention to, well, only, first of all, don't represent the entire DDG, because we put only nodes that have, that attaches memory, so load stores. And then furthermore, before we start to really traverse the graph and partitioning, we reduce the graph, we increase the granularity of the node by the strategy of merging nodes. And so we are running these on large benchmarks. I'm not sure if I can really mention, but yeah, we're running this on real code. And yeah, we're also tracking the, of course, you know, the work in progress, but we're trying to track the compile time effect that, first of all, building the DDG and also the FIG have on those benchmarks. There is a lot more work to be done. But I'm not sure I understand fully, like you're trying to say, maybe we should have a view on top of the DDG instead of creating new nodes.
No, I think the iterating over all pairs of something is wasteful and should almost be never ever be done. There's for the DDG, there's an argument to do it because the interface of the dependence info doesn't allow you basically to do anything else. It takes two instructions, and you have to do compare. Basically, you have to do the compare, call it pairwise to get all the dependencies. But once you have that, this should never happen again. It's always been done. So in this case, in the fission interference graph, it's easily avoidable by iterating over the already existing nodes and edges over the loop interference graph, then basically trying to reconstruct it from scratch again. So it's just not necessary to have an n squared, or it was even worse, n squared times e or something, complexity there. So I assume, so I could, if you do it in a real code, I can probably construct something where we just have, I have just enough independent components that could be fissioned and not merged into a pi node. So I think at one point we will hit that and require some kind of bailout, since then n squared usually it will occur sometime.
Okay, so I think that I have an idea of what is of the code. Sometimes we did go through the graph in the interference after merging. We go through and say, well, traverse this, and then maybe we're trying for nodes that have a edge of a certain type, and then we traverse it again and we try to figure it out. So there may be better algorithm to do this. I would appreciate, as you guys go through the code, if you can help to point out the places where there is a problem or even a perceived problem, and then I'll try to work with you to see if we can find something faster, better.
Okay, thank you.
Okay, any other comments or questions? All right, and thank you very much for joining. Talk to you next time.
Thank you. Bye. Have a great day.
Bye-bye.